Hello everyone, welcome to SciMath. Today we are going to solve the 2013 F equal to MA exam. As last time, we have 25 questions and 75 minutes to complete it. Because it's an instructional video, we are going to explain each of the problems, so we probably will take a little bit longer. So here's the instruction, and let's begin. So the first problem, an observer is standing outside of a shrunk stationary train. When the train is traveling with constant acceleration from rest, it takes 5 seconds for the first car to pass the observer. How long will it take for the 10th car to pass? So we have a train. We have lots of cars. There's first car, second, all the way to the 10th. And here's the observer standing still, watching this train pass by from rest to constant acceleration. So for the first car to pass the observer, it takes 1/2 at squared equal to L. We can use this equation to describe the length and the time, using time and acceleration to describe the length of the first L. First, each of the length of each car. Then we know t is equal to 5 seconds, so a times 25 over 2 is equal to. So what is acceleration? Is equal to 2L over 25. And 2L over 25 will be the acceleration of the train throughout the process. So when we find the 10th car, how long will it take for the 10th car to pass the observer? We need to find how long does it take for this segment of the train to pass the observer minus this segment to pass the observer, so that the remaining time will be time of this car. Very simple, right? So again, we use our kinematic formula starting from rest. So 1/2 a t1 squared. T1 stands for the time it needs to pass 9 cars, so times 9L, and 1/2 a t2 squared is equal to 10L. So now let's plug in a to solve for t1 and t2 and find the difference so we get our answer. So we have 1/2 times 2L over 25 times t1 squared equal to 9L. L cancels out, 2 cancels out, so t1 is equal to 3 times 5, which is 15. Then what is t2? T2 the same thing. T2 is equal to 250. The square root is 250. And what is the square root of 250? Let's calculate with our calculator. The square root of 250 is equal to 15.811, something like that. 15.811. And 15.811 minus 15 would be 0.81. So that will be our answer, E. So the second question. Jordi stands 20 meters from the wall and Diego stands 10 meters from the same wall. Jordi throws a ball at an angle of 30 degrees above horizontal and collides elastically with the wall. How fast does Jordi need to throw the ball so that Diego will catch it? Consider Jordi and Diego to be the same height and both are on the same perpendicular line on the wall. So here we have Jordi and here we have Diego. And here's the wall. The distance between them is 10 and 10. 10 from here to here. Totally will be 20 because Jordi is 20 meters from the wall. Then Jordi will throw a ball all the way, hit the wall, and bounce back to Diego so that Diego can catch it. So what is the velocity of the ball so that Diego will finally catch the ball? Its launching angle is 30 degrees. Right, 30 degrees. So in this problem, we can use the principle of symmetry. Since the collision here is elastic, so there's no energy lost, and momentum conserved, and energy conserved, so we can imagine there's an extended line over here, and here is our imaginary Diego catching the ball, also 10 meters away from the wall. So we have So all we need to know is the flight of this path instead of this path, because the velocity required to make both paths are identical. So what is the minimum velocity required for this flight? We have a kinematic formula. We have cosine of 30 degrees times the velocity we need times time, have to equal to 10 plus 10 plus 10, which is 30 meters. Then what is the time required? Time will be twice the time for the ball to reach its highest point. So it will be 2 times v sine 30 degree over g. That will be equal to time. So we plug it in. We have 2v times cosine theta will be 3 over 2 times 1/2, and over g, that will be equal to 30. So what is v? 2 cancel out. We have 30 times g is 300 times 2 is 600 over square root of 3, and then all of them square root. Sorry, there's a square sign here. And what is that? That will be equal to let's calculate with our calculator. 600 over the square root of 3, and then square root all of them. That will be equal to 18.61 something, which is closest to 19, which will be C. So question number 3. Tom throws a football to Wes, who is a distance L away. Tom can control the time of flight t of the ball by choosing any speed up to Vmax at any launching angle between 0 and 90 degrees. Ignore air resistance and assume Tom and Wes are at the same height. Which of the following statements is incorrect? Remember, incorrect. So let's see each of the options. First, A. If Vmax is smaller than the square root of GL, the ball cannot reach Wes at all. So here we have 2 persons. One is Tom, one is Wes. And the distance between them is, let's say L. It says L. And the launching angle can be any chosen, and there's a Vmax, maximum speed. So let's use our projectile motions equation for the distance to solve for whether Tom can what are the necessary conditions for Wes to catch the ball from Tom. So we have 2v squared times cosine theta times sine theta over g is equal to L. Then let's say we want to find whether Vmax have to be smaller than VL. Well, let's say VL square root will be equal to 2 square root times V times cosine theta times sine theta, all of them square root. So okay, in here, if Vmax is smaller than this one, then can the ball reach Wes at all? Here we know cosine theta times sine theta is an extremely small number, and we want to square root it, it will be even smaller, and the square root of 2 is very close to 1. So for a very, very small constant that's smaller than 1, a constant is smaller than 1 times V have to equal to GL. So V have to a lot bigger than GL in order to balance the equation. So if Vmax is smaller than GL, it's never gonna work. It's never gonna reach. The ball is never gonna reach Wes. So statement A is correct. We want to find the incorrect one. Remember. So let's see it. Option B. Assuming the ball can reach Wes as Vmax increases with L fixed, the minimum value of T decreases. Well, this is a pretty intuition, because if we throw the ball at a faster speed, of course the minimum value of T will decrease, right? This is pretty intuitive, so B have to be correct. Assuming the ball can reach Wes as Vmax increases with L fixed, but the maximum value of T increases. Okay, so this is a little different than the first one. The first one, we assume that the velocity is maximum, so we throw at a maximum speed so that we minimize the time. But the second one, we want to find the maximum value of T. So we have to throw in higher speed, but also in different angles. The first one, we just lower the angles. low as possible, so the minimum value of t is decreasing because v is increasing. But second one, because v increases, we can also make it available for the launching angle to be bigger, so that we throw the ball higher, make the parabola thinner and higher, so that we can make the maximum value of t greater and greater, as you can imagine. So C is also correct. And D, assuming the ball can reach west, as L increases with Vmax held fixed, the minimum value of T increases. Well, let's imagine if L is increasing but the maximum velocity is fixed, the minimum value of T increases. Well, of course, because if you make the velocity fixed and you increase the distance, the time will also increase, minimum time will increase. That's very intuitive. So D has to be correct. And E, assuming all the ball can reach west as L increases with Vmax held fixed, the maximum value of T increases. So again, in the option D, we are talking about the minimum value. Now in question E, option E, we're talking about the maximum value of T, which we need to control the launching angle. So as L increases, in order for West to catch the ball, but with a velocity that's fixed, we have to throw the ball at a lower and lower angle. And as long as we are throwing the ball at a lower and lower angle, we are going to decrease the maximum time. Not increase, but decrease. But he said increase, so this is wrong. So the incorrect one will be option E. Now let's look at the fourth one. The sign shown below consists of two uniform legs attached by a frictionless hinge. The coefficient of friction between the ground and the leg is mu. Which of the following gives the maximum value of theta, such that the sign will be collapsed, such the sign will not be collapsed? So here, let's write out all the force here, as we know this is a static force problem. So we have a normal force here, a friction force, normal force. Because this triangle is symmetry, so we only look at left-hand side of the stick, left stick. So we don't have to write everything out. There's also another normal force, this is normal force 2, this is normal force 1. And there's a gravitational force, mg, acting up here. So now we can balance the force. This is theta, so this will be theta over 2. So let's use our torque. If we use this point, let's say this point is point O as our pivot point of the torque equation, then we will have N2 times L. L is a distance length of this stick. N2 times L have to equal to mg times this angle times sine of theta over 2. Okay. And also, because since this is a static force problem, the horizontal component and the vertical component have to be cancelled out. So the horizontal component N2 have to equal to the frictional force F, and N1 have to equal to mg. Since N2 is equal to F, we can replace N2 here with F. And what is the friction? Friction is equal to, well, as we know, the normal force N1 times mu times which is the frictional force, right? So N1 times mu times L is equal to mg times sine theta times L over 2. And we know N1 is equal to mg, so we can plug in mg here. So mg times mu times L equal to mg times sine of theta over 2. Oh, also we forgot L over 2, because mg is in half distance at the center of mass of the stick, which is half from another end of the stick. So let's cancel out some term. mg cancel out, mu l cancel out. So sine of theta over 2 will be equal to 2 mu. Then what is sine? That is interesting. Oh, we also forgot something. This is not true. This is not true because we forgot that we need to multiply by another angle. This is another angle. It's alpha here. We all forgot to consider the angle for the normal force and 2. So alpha is equal to 90 degree minus theta over 2. So here we need times theta over 2, 90 degree minus theta over 2 times sine. So sine of 90 minus theta over 2 times this one, which is equal to cosine of theta over 2, So here we also need to add, actually here we need to cosine of theta over 2. Then we simplify the equation. mg cancel out, ll cancel out. We have mu is equal to sine of theta over 2 divided by cosine of theta over 2 times 1/2, which is equal to mu is equal to tangent of theta over 2 over 2. So 2 mu is equal to tangent theta over 2. So this will be E. The fourth question will be E. Okay, now let's look at the fifth one. The fifth question and sixth question are giving the same information. So a student steps onto a stationary elevator and stands on a bathroom scale. The elevator then travels from the top of the building to the bottom. Student records the reading on the scale as a function of time. So in here we can see there's acceleration downwards, so the student gets lighter, and then there's a constant speed. And then at time 22 to 24, the elevator is going to stop, so it's an upward acceleration. So the scale of the weight of the students goes up. It's pretty interesting, as you can feel in elevator. It's very common. So, in question 5, at what time does the student have maximum downward velocity? Well, since the only positive accelerating time is from here to here, so after time 4, from the 4 seconds, the elevator stops accelerating and remains a constant velocity, as we see here. So the scale didn't change until here 22, which acceleration changed again, and this time it's countering the velocity. So at all time before 4 and 22, the velocity is at maximum. So the answer is C. Now the sixth one, how tall is the building? Oh, that's an interesting question, because here we need to know both the acceleration of the elevator and the velocity it reached from 4 seconds to 22. How tall is the building? So here we need to find acceleration. And here, how much weight? Let's notice how much weight does the student lost in the downward acceleration. Well, 80 minus 60 is equal to 20 kg. It's lost. So there are 200 newtons of inertia force caused by this downward acceleration. And what is this force for F equal to ma? This is inertia force. Remember, inertia force is imaginary. It's not something that's real, because the changing reference frame is caused by the changing reference frame. So 200 newtons is equal to the mass of the student times acceleration. The mass of student is 80 kilogram, because that's what its normal weight beginning when the elevator is not accelerating, times 8. So acceleration will be equal to 200 divided by 80, which is 20 divided by 8, which is 5 over 2, which is 2.5 meters per second. So from here to here, it takes 1/2 AT squared is equal to L. So what is A and what is T? T is equal to 2, because it takes 2 seconds to accelerate to the maximum velocity. So 1/2 times 2.5 times 2 to the square is 4. It's equal to L. So L is equal to 10 over 2, which is 5 meters per second. Then, for all time between 4 seconds and 22, we have 18 times 5, which is equal to 90 meters. 90 meters from the bottom, 90 meters until it tries to stop. Okay. Oh no, this is not true, because L is the distance, it's not the velocity. So it travels 5 meters in this process. So the time is equal to 2, acceleration is 2.5. So what's the velocity it reached? From 0 to 2, from 2 seconds to 4 seconds, experience 2 seconds of acceleration. So 2.5 times 2 is equal to 5 meters per second. Oh, so we are right. Distance to travel and the velocity have the same numerical value. Okay, so 5 times also 18 is equal to 90 meters. And also at the end, it also accelerating as in the opposite direction for the same period of time. So they should travel the same distance. Here travel 5 meters, here travel 5 meters, here travel 90 meters. So 5 plus 5 plus 90 is equal to 100. So this question should be C. And question number 7. A light car and a heavy truck have the same momentum. The truck weighs 10 times as much as the car. How do the kinetic energy compare? So a light car has a mass. Light car has mass m. M 1/2 n v squared. This v is a big V. Is equal to no. This is the kinetic energy of the car. And the 1/2 m little v squared is the momentum and kinetic energy of the truck. The little v times v have to be equal to big V times small v, because the momentum are the same. So let's plug them in. We know the heavy truck, a light truck can have the same momentum, but the truck weighs as twice the time as the car. So mv have to equal to 2 times m times little v. So m cancels out. We know v is equal to 2 little v. So here we will know the car has kinetic energy 1/2 m 2v all of the square, which is equal to 1/2 m times 4v squared. 4 and 2 cancels out, left the 2, so 2m little v squared. What about the second one, the big truck? We have 1/2 times m times v squared, which is equal to 1/2 times 2m little m times v squared, because big M changed to 2m. The truck have twice the mass of the little car, so we have mv squared. So the kinetic energy of the car is twice the kinetic energy of the of the truck. Oh no, it's 10 times, not 2 times. Sorry, this is 10. This is 10, then this is 10, and this is 100 over 2, which is 50, and this is 10, this is 5. Okay, so the kinetic energy of the car is 10 times the kinetic energy of the truck. So the car's kinetic energy is larger by a factor of 10. Yes, this is true. D. So now let's look at A's problem. A's problem. A truck is initially moving at a velocity v. The driver presses the brake in order to slow the truck to a stop. The brake applies a constant force F to the truck. The truck goes the distance x before coming to stop, and the time it takes to stop is t. So number 8, which of the following expression is equal to the initial kinetic energy of the truck? The kinetic energy before the driver starts braking. So we know force is equal to the work is equal to force times distance, very simply. So it's A. And question number 9. Which of the following expression is equal to the initial momentum of the truck? Momentum before the driver starts braking. Okay, this is very interesting because we need to find a relationship between the momentum and the kinetic energy of a given object. So momentum is mv, and kinetic energy is 1/2 mv squared. So all we need to know is the kinetic energy, energy divided by velocity times 2 will be equal to the momentum. And we know kinetic energy, K, as we calculated before, is equal to Fx. So Fx over V times 2 will be equal to our momentum. Right? Is that correct? So here we have 2 Fx over V. That will be our momentum. Question number 10. Which of the following can be used to distinguish a solid ball from a hollow sphere of the same radius and mass? A measurement of the orbit of a test mass around the object. The measurement, is that right? Orbit of a test mass around the object. Well, if we are considering our solar system, are we going to consider whether the sun is hollow or a sphere? No, in celestial body, we just consider the point mass. Because in orbit it's big, we don't consider the shape of the object or how hollow it is. The angular the moment of inertia doesn't affect the orbit. So A is not correct. B. Measurements of time it takes for the object to roll down the inclined plane. Also, this does not depend on the moment of inertia. It only depends on the radius and the mass. And since their mass are identical, the radius are the same. Just the difference is they're hollow and solid. This is also incorrect. So C, the measurements of the tidal force applied to object to a liquid body. Well, this is the same thing also, because we know the Newton's shell rule, the gravity inside a sphere is 0, and gravitational force inside the shell is 0. So it behaves the same on the surface, where Earth is a hollow sphere or it's a solid sphere. We all feel the same tidal force. So C is also not correct. D, the measurements of behavior of objects as it floats in water. This is also not true, because the buoyant force also depends on the volume of the repulsion of the water, the volume of the water that's being repulsed by the object. And they have the same mass and the same volume, so D is also incorrect. E, measurements of the force applied to the object by a uniform gravitational field. Well, I think this is also incorrect, because uniform gravitational force only acts on the point mass, right? we consider it as a point mass. So E is also incorrect. Well, this is strange. Which one did I miss? Maybe let's relook at D. A, C, D, E are pretty obvious to be wrong. Maybe D, B can be distinguished. Okay, the moment inertia does matter. Moment inertia does matter because the moment inertia is different, then it applies different torque to the object when they're rolling down an inclined plane. And the hollow sphere have a higher moment inertia than the solid sphere, so hollow sphere will roll slower than the solid sphere. So B should be the answer. Okay. In 11, a right triangular wooden block of mass m is rested on the table, as shown in the figure. Two small wooden cubes, both with mass m, initially rest at two sides of the larger block. As all contact surfaces are frictionless, the small cube starts sliding down the large block, while the block remains at rest. What is the normal force from the system to the table? From the system to the table. Okay, so let's write out our force here. There are three forces: mg, mg, and mg. First, we want to consider normal force. Let's see the whole system as a whole. What is the acceleration of the center of mass of the system compared to its normal force? So we know m plus 2m times the acceleration of its center of mass have to equal to m plus 2m times g minus the normal force. Is that correct? And we have a downward acceleration, then the actual normal force we feel should be less than what is all at rest, because the cubes are accelerating downwards, right? So what is the acceleration of its center of mass? Well, let's see here, because here we have mass m accelerating in this direction. We can use a trigonometric formula. The downward acceleration is g, but it's restricting to this boundary, so g to be times a sine of alpha. Oh, same thing applied to this m. This m accelerating in this direction, so that g times sine of beta. And we need 2 of acceleration plus together, because these two are in the direction of these two acceleration are not perpendicular to the normal line, to the horizontal line. So we also need to make them find the perpendicular component. You find the acceleration of central mass perpendicular downwards. So we also need to multiply this by another sine of theta. This is also another sine of beta, because we now have this component. We also need to convert this to this component again. So m times the acceleration plus m times this acceleration divided by the total mass is 2m plus m, have to equal to a. So now we plug in a to this original equation. We cancel out this term. We have m times g times sine theta square plus m times g times sine beta square is equal to m plus 2m g minus m. Now because theta and because alpha and beta are their sum are equal to 90 degrees, because it is a right triangle. So sine of beta is also equal to cosine of alpha. So sine of alpha square plus cosine of alpha square have to be equal to 1. So here we simplify the equation to m times g have to equal to m plus 2m g minus n. So what is n equal to? Well, mg is equal to m times g plus 2mg minus n. So n is equal to mg plus mg. What is mg plus mg? Here, C is the answer. Okay, let's look at the next one. 12. A sphere shell of mass m and radius r is completely filled with frictionless fluid, also mass m. It is released from rest and then rolls without slipping down an incline at a mixed angle of theta with horizontal. What will be the acceleration of the shell down the incline just after it is released? Assume the acceleration of the free fall is g. Moment inertia of the shell, radius r and mass m about the center of mass is I equal to 2 divided by 3 times mr squared. Moment of inertia of a solid sphere of radius r and mass m about the center of mass, I equal to 2 divided by 5 times mr squared. Okay, since the fluid is perfectly frictionless, so it's not rotating, so we don't need to consider the moment inertia of the solid sphere. All we need to consider is the hollow sphere. And also, we can use the parallel axis theorem to find out the how would the hollow sphere, the moment inertia be. With hollow sphere rolling down the incline with acceleration, we have all the work because it's rolling without slipping. So all the acceleration is equal to omega times r. So this is r, and this is a normal force, and there's a friction force. Friction force keeps the ball rolling. So here's how we're gonna find it. We know that the torque of this object, Fr, is equal to the moment inertia times its angular acceleration. So angular acceleration times moment inertia. Moment inertia is equal to 2 times 2 over 3 m squared. Actually 2m, because 2, yeah, I already put it here. We don't need to consider this because it's a hollow sphere. We only need to consider moment inertia of hollow sphere, and the water is not rotating. So we can cancel out some terms. R and R cancel out. R and alpha become to A. So 4A times 4 over 3 times M will be equal to the friction force. So what is the friction force? Friction force will be equal to mg times sine theta. Well, we forgot to say this is theta. Sine theta times mu is equal to A times 4 over 3 times M. M and M cancel out. Now let's assume the mu is equal to 1. So we have g times sine of theta is equal to A over 4 times 3 over 4. So 3 over 4 g times sine theta is equal to A. So the answer is B. And question number 13. There is a ring outside of Saturn. In order to distinguish if the ring is actually part of Saturn or is instead part of the satellites of Saturn, we need to know the relation between the velocity v of each layer in the ring and the distance r of the layer to the center of the Saturn. Which of the following statements is correct? So let's imagine if the ring is part of the Saturn, that they will have the same angular velocity, which means the bigger the radius, the velocity of the Saturn's ring will be directly proportional. And if the ring is not part of the Saturn, then the velocity of the ring will be obeying the gravitational law. A. If V is directly proportional to R, then the layer is part of Saturn. Well, that is correct, right? That's correct. So I think the answer is A. But let's look at the rest of the option to make sure. So if V squared is proportional to R, then the layer is part of the satellites of the Saturn. No, it should be 1 over V squared, not just V squared, right? Because we want to know the centripetal force V squared over R times M have to equal to G times MM over R squared. So V have to be directly proportional to 1 over R, not R. And if V is proportional to 1 over R, the layer is part of the Saturn. Nope, this should be directly proportional. And V squared is directly proportional to 1 over R, the layer is part of Saturn. No, it should be on the satellites of Saturn. And E, if V is directly proportional to R squared, then the layer is part of the satellites part. Nope, it's not. V have to be proportional to the 1 over the square root of R, right? So let's look at question number 14. A card of mass M is moving at 12 meters per second to the right, collides elastically with a card of mass 4 kg that's originally at rest. After the collision, the card of mass M moves to the left with a velocity of 6 meters per second. Assuming the elastic collision is one-dimensional only, what is the velocity of central mass of the two objects before the collision? Okay, so in this problem, we have two cars. One car is moving 12 meters per second to the right with mass M, and another card with mass of 4 kg moving to the left. Oh no, it's not to the left, it's originally at rest. So after the collision, the card of mass moving to the left is moving velocity of 6 meters per second, and right is moving to the right clearly at V. So now we can solve for the velocity of the second card and a mass of the first card. Actually, what we want to know is the mass of the first card, so that we can know the center of mass velocity before the collision. So let's use our laws for the conservation of momentum and conservation of energy. So M times 12 have to equal to M times 6. No, have to equal to 4 times V minus 6 times M. Right. So 6 times, so plus both sides by 6M, so 18M have to equal to 4V. So V is equal to 18M over 4. That will be equal to the velocity of the second card after the collision, to the right, actually. And what about the mass of the first object? Let's use our conservation of energy, since the collision is elastic. So 1/2 m12 squared is equal to 1/2 4v squared plus 1/2 m6 squared. Multiply both sides by 2, so we have 144m have to equal to 2v squared plus m times 36. So 144 minus 36 equal to 108. 108. M is equal to 4v squared. Then we plug in V is equal to 18m over 4. So 4 times 18 squared m squared over 16 is equal to 108 m. So now we just need to solve for this m cancels out. We have 18 squared over 4 times m is equal to 108. Okay, so now let's just plug in our calculator to find out the result. So 108 times 4 over 18 squared is equal to 1.33. The mass of the object is 1.33 kg. So 1.33 times 12. Now we want to find the central mass acceleration. 1.33 times 12 divide by 4. 4 plus 1.33. What is that equal to? 2.99. So the center of mass speeds should be 2.99 to the right. That will be closest to 3, of course. The answer is B. And 15. 15 will be have a lot of calculation. A uniform rod is in water with one end suspended as shown in the figure. The density of the rod is 5 over 9, that of water. The equilibrium. What part of the rod is above water? So in this question, let's assume this part of the rock X and this part of the rock Y. X is the part of the rod that's above the water, and Y is the part of the rod that's below the water. And the center of mass of the rod below the water is at half of the points, is at half of the distance from the other end of the rod to the all the way to the section of the rods below the water, and that will be our buoyant force, of B, buoyant force. And this will be our gravitational force, acting center mass of the entire rod, F of G. And because the static torque should be equal, and here we go how we're gonna solve for it. So we want to balance the torque. We have listed out a torque equation. So Fg times L over 2 have to be equal to F of B times L over 2 plus L minus X over 2, right? L over X equal to Y. Yeah, Y. Because, okay, so let's explain what is determined. L over 2 here is distance from here to here is L over 2. Distance between here to here and here to here are the same, and that should be L over X, which is Y, and 1/2 of the Y will be a distance from the center of mass to the center of buoyant force. So here we go. Now we just solve the equation for X. What is Fg? Mg is equal to M. The force of gravity is mg times L over 2 is equal to F of buoyant force is equal to the water repelled by this thing, which is all L over L minus X, the volume times the density, times the density of the water, which is rho of water, let's say, rho of water, times L over 2 plus L minus X over 2. Ooh, this is a big chunk. And now let's do it a little more. We know the mass is actually equal to density times volume. So the volume, we just ignored the rod's radius, because radius are the same. So later on it will cancel out. So we only consider the length as our volume. So we have mg is equal to rho of water times 5/9 times g, that's L over 2, have to equal to L over x times rho of water times L over 2 plus L minus x over 2. So these two terms cancel out. G cancel out. Oh, there should be a G cancel out. Now multiply both sides by 2. We have 10/9 L. Oh no, we don't need to multiply by 2. This is still 5 because here's a 2. I forgot to look at it. Here's a 2. We forgot to look at it. Add to equal to L minus x times L plus L minus x. So equal to, so 15/9 L have to equal to L minus x times L. So L squared minus XL plus L minus x squared. What is L minus squared? So L squared minus XL plus L squared minus 2XL plus x squared. So this will be 2L squared minus 3XL plus x squared. So 15/9 L. So now we solve for the x. Let's multiply both sides by 9. So we have 15L is equal to 2 times 9 is 18L squared. 18L squared minus 27XL plus 9x squared. Okay. So now let's solve for x. So 9x squared minus 27XL plus 18L squared minus 15L have to equal to 0. So now let's plug in our quadratic formula. We have 27L plus and minus the square of 27. Square minus 4AC. 4 times A is 9. 9 times 4 times 18L minus 15XL. So this is very messy, so the final result will be L times 2/3 equal to x. L times 2/3 equal to x. So the answer should be D. It's very messy calculation. Probably made a mistake, but probably the first time I got the answer is L times 2/3. And that's what the solution menu said. Okay. And question number 16. A very large number of small particles forms a spherical cloud. Initially they are at rest. A uniform mass density per unit volume, rho naught, and occupy a region of radius r naught. The cloud collapses due to gravitation. The particles do not interact with each other in any other way. How much time passes until the cloud collapses fully? But this is a dimensional analysis problem. So all we need to know is there are three constants, three units we need to manipulate. The radius, the gravitational constant, Newton's gravitational constant, and the density. So radius has a dimension of L, length. The gravitational constant have the dimension of L cubed over mt squared, and rho has the which the density as the unit of mass over L cubed. So this is all known. To the A power, to the B power, to the C power have to equal to time, because all we need to find is the time of the collapse. So after some dimensional analysis, we know B have to equal to C, because L to the 3 divided by L to the 3. So B power to C power have to cancel out because there's no L here. So B have to equal to C. Oh no, that's actually not correct. Oh yes, but it's not because the L, it's because the M. So mass to the V's power, negative B power, times mass to the C power have to cancel out. So B have to equal to C. And also A plus 3B have to equal to 3C. So A have to equal to 0 because B equal to C. A is equal to same. A is equal to 0. So so there shouldn't be any problem with the radius. So in all the options, there's only one option, which is option D, does not have a radius in the answer. So D will be the correct answer. Okay. So 17. Two small equal masses attached by a light-weighted rod. This object orbits a planet. The length of the rod is smaller than the radius of the orbit, but not negligible. The rod rotates about its axis such that the weight remains vertical with respect to the planet. Is there a force in the rod? If so, is the tension or compression? And the equilibrium state unstable or neutral with respect to the small permutation and angle of the rod? Assume the permutation maintains the rate of the rotation, so that the co-rotating frame of the rod is still stationary, but an angle to the vertical. So first, is there a force in the rod? Well, because one of the ball object, one of the mass has a higher radius than the second mass, so there has less gravitational attraction to it. And since they all have the same angular velocity, the mass on the outer radius to experience a higher centripetal force. So of course, there is a tension in the rod. So we all wrote down to B and C. Now just we understand whether the equilibrium state is stable or unstable. If you have a little permutation to this system, let's push it here, so it will bounce, so it will tune a little bit angle. Then what will happen? Because as we know, there's a tension in the rod, because there's a higher centripetal force on the outer object than the inner object, and there's a weaker gravitational attraction to the outer object than the inner object. So there will be a force acting this way, force acting on this way, and it will bring the orbit back to normal. There's a restoring torque to the system. So the equilibrium state is stable. So 17 is B. Now let's look at question number 18. So 2 point particles which are mass 1 kg. The state is shown below, as you see here. The system evolves through internal force only. Which of the following could be the state after some time has passed? So at the beginning, we see this configuration of particles moving in the opposite direction. So if we experience inertial force, the momentum have to be conserved, and the energy have to be conserved. And also the center of mass has to be unchanged. The position have to be unchanged. So clearly we ruled out A and B because A has moved the center of mass. Center of mass is not here to be here because the mass here should be there. And here the momentum clearly not conserved. And here all conserved. Here, the center of mass are the same position. And now we also need to consider the angular momentum have to also be conserved. Because here we see a greater lever arm from the center of mass of the system. So angular momentum should be higher, but that's not possible because the internal force will not change the angular momentum. So D is false. Also C, because the direction of the particle's movements is not perpendicular to the horizontal line. So the angular momentum will be smaller because the little angle between the velocity and the lever arm. So C is also not correct. So only thing comes down to E. The momentum is conserved, angular momentum is conserved, and also the position of the center of mass has not changed. So the answer is E. Now look at the 19th problem. So what angle? We should read the information first. The simple pendulum experiment is constructed from a point mass M attached to a pivot by a massless rod of length L in a constant gravitational field. The rod is released from an angle theta is more than pi over 2 at rest, and period of motion is found to be T naught. Ignore air resistance and friction. Question number 19. At what angle theta will the swing is the tension in the rod be the greatest? So of course it's when theta t equal to 0, because that's when the velocity of the mass be the greatest, so the centrifugal force is the greatest, and also the gravitational force is perpendicular, acting directly down. So the two forces act together, they should be the greatest. So 19 should be B, very obviously. And question number 20. What is the maximum value of the tension in the rod? This will be a little bit hard to calculate. So first, let's consider what is the velocity. We need to consider two forces as acting on the pendulum. This is our pendulum, and from here to swing all the way to here. Two different forces acting on it. First is the gravitational force. Second is the centripetal force. The centripetal force depends on the velocity squared over L. L is the length of the rod. So what is its velocity? Square. We can starting to think about it from the conservation of energy. All the potential energy in the system conserving the kinetic energy. So 1/2 mv squared have to equal to mg h. What is h? H is equal to L times, let's say this is theta 0, starting with angle of theta 0, L times cosine of theta 0, L minus L times cosine theta 0 times mg. M and M cancel out, so V squared equal to 2 times L times 1 over 1 minus cosine theta over 2 times G. So now we need to add them together. So m times v squared over L plus mg is equal to m times v squared, which is equal to 2L times 1 minus cosine theta, not over 2. There shouldn't be over 2. I don't know why I wrote over 2 times g plus g. And this should be over L, so L should be cancelled out. Okay, so this one should be equal to m times 2 minus 2 cosine theta times g plus g. Then we can add this to 3 and minus negative g. So m times 3 minus 2 cosine theta times g will be the answer. So the answer will be m times g times 3 minus 2 times cosine theta. Okay, question number 21. The experiment is repeated with a new pendulum with a rod of length 4L, using the same angle theta. And the period of motion is found to be t. Which of the following statement is correct? Well, we know no matter how we choose the angle of the pendulum will always be, the period of the pendulum will also be t equal to a function that's related to the angle, to the angle theta times L over m over g and an element square root. So this is a dependent function about the theta, but about the theta and L and g. But since we are keeping theta fixed at each of the experiment, but only L is the one that's varied. So if we change the rod of length to 4L, then the period will be just be 4 square root of 4, which is equal to 2. So A is always correct, no matter what we choose the value of theta or not, because we already considered this to be a fixed value in each of the separate experiments. So question number 22. Question number 22. A simple model on the foot of shown. When a student of mass m equal to 60 kg stands on a single toe, the tension T in the Achilles tendon is closest to what? So this is a very simple torque problem. So here we see the distance from here to here is equal to 5 centimeters. And distance from here to here is approximately 20 centimeters. So as we know, it's 60 kg, so approximately 600 newtons of force times 20 cm have to equal to another tension force times 5 cm. So 600 times 20 over 5, which is equal to t. So 12,000 over 5, which is equal to t. So t is equal to 2,400. T is equal to 2,400, which is dog. Dog is the answer. Okay, question number 23. Following information applies to question number 23 and 24. A man with mass m jumps off a high bridge with a bungee cord attached to his ankles. The man falls through a maximum distance h, at which point the bungee cord brings him a momentary rest before he bounces back up. The bungee cord is perfectly elastic, obeying the Hooke's law, with spring constant k, and stretches from an original length of L naught to a final length L equal to L naught plus h. the maximum tension in the bungee cord is 4 times the weight of the man. Determine the spring constant K. Okay. Maximum tension in the bungee cord 4 times the weight of the man, which is when the bungee cord is at maximum stretch. So here is the bungee cord. Here is our little man. Let's write this man as that. Okay, it's very poor man. So here is the original length of L, and here is H. So as we know the Hooke's law, the change in the length of the cord times K is the spring constant have to be equal to, we said, the tension in the bungee cord is 4 times the weight of man. 4 times the weight of man is 4 times mg. Okay. Okay. The man falls through a maximum distance h. A point bungee cord brings him to a rest. So also we can use our conservation energy. mgh have to equal to 1/2 k little h square. So now what is h? Well, h is equal to 4 mg over k, and mgh is equal to 1/2 times k times h squared, which is 16 times m squared g squared divided by k squared. So k cancel out, m cancel out, g cancel out, 1/2 can cancel out with 16 to become an 8. So h is equal to 8 times mg over k. So k is equal to 8 times mg over h. It's correct. So the answer will be E. E will be the answer to this question. Okay, now 24. Number 24. For the maximum tension of bungee cord H. Well, since we already know the spring constant, and we want to know how much does the cord stretch, which is 4 times the weight of the man. So H times K is equal to 4 mg. K, as we know, is equal to 8 times mg over h, is equal to 4 mg. And little h, what is little h? Little h is equal to 4 mg divided by k. Well, what is little h? This is an interesting question. What is little h? Oh, that's what we are trying to solve. So little h is equal to 4 mg times h over 8 mg. mg cancel out, 4 and 8 become 1 over 2. So h is equal to 1 over 2 big H. 1 over 2 big H. So question number 24's answer will be A. So exactly, the bungee cord is very elastic. Extend twice of its length in order for the man to slow that man down. Okay. So question number 25. A box with weight W will slide down 30-degree incline at a constant speed under the influence of gravity and friction alone. If instead a horizontal force P is applied to the box can be made to move up a ramp at a constant speed. What is the magnitude of P? So here we have an incline, and there is a mass moving downward. This is 30 degree. Actually, it's 30 degree. 30 degree. And this mass is moving down the inclined plane like that. This is its normal force. This is its component of gravity being separated in horizontal and vertical direction to the surface of the plane. Then we can calculate what kind of magnitude P here are we going to consider in order to push its upward with constant velocity. Constant velocity means just like static force. Make the force equilibrium. Yeah, equilibrium. So here we go. First, before it goes down, we know before the force is applied, it's already a static force. So mg times cosine 30 degree times mu have to be equal to mg times sine of 30 degree. The horizontal component of acceleration downwards have to be equal to the vertical component, the opposite direction of the friction force applied, which is equal to normal force times mu. So mg cancel out. Mu is equal to sine 30, which is 1/2, divided by 3, square root of 3 over 2, which is 0 root of 3 over 3. That's the coefficient of friction that we saw. And now after we applied force P in this direction, so we have our horizontal component being still the same, which is mg times sine of 30 degree, but equal to mg times cosine 30 degree plus a p, which is the magnitude of this horizontal force, times 90 minus 30, which is 60 degree. Oh no, the cosine of 60 degree. I also need to plus a upward force in this direction, which is cosine of 30 degree times p. And now let's solve for p. So mg divided by 2 have to equal to mg times square root of 3 over 2 plus p times 1/2 plus square root of 3 over 2. Multiply by 2 from both sides. So mg is equal to mg times square root of 3 plus p plus p times square root of 3 over 2. So mg 1 minus 3 have to equal to p times 1 plus 3 over 2, square root of 3 over 2. So what is p? P is equal to, oh, we all forgot to multiply by this by mu. Okay, so there's a mu, 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 and there's no 2 anymore. There's a mu. So p is equal to mg times 1 over square root of 3 times mu divided by mu minus square root of 3. Oh, not mu minus, mu plus square root of 3. Right. Oh no, square root of 3 minus mu. Oh no, mu plus square root of 3. Okay. So what is mu? We just solved mu is square root of 3 over 3. So 1 minus 1 more square root of 3 times square root of 3 over 3, which is equal to 0. No, this is not correct. I must make a mistake here. Let's see what I made mistake. Over here, mg times sine theta. Oh no, mg times cosine theta plus p times cosine of 60 degree. and 30 degrees. Maybe this should be a minus sign because the friction force is always against the direction of the object's movement. So now we mess them all up. So let's just recalculate them all here. So mg times sine of 30, which is mg over 2, is equal to negative mg times 30 over 2 minus p times 1/2 times mu plus p times 30 over 2. Okay. Now we have mg times 1 plus 3. 1 plus this for the mu is equal to p times, we multiply both sides by 2 and then move the terms around. It's mu. So p is equal to mg times 1 plus 1 divided by 0.3 minus 0.3 over 3, which is equal to 3 times square root of 3. From 3 minus 3 is equal to 2 times square root of 3 over 3. And this is mg times 2. 2 cancel out. 3 mg times 3 divided by square root of 3, which is square root of 3 times mg. Square root of 3 times mg, which is the square root of 3 times the weight w. W is right here, and 3 times square root of 3 is d. So 25 should be equal to d. Okay, and that's all the problem in F equal to MA 2013 exam. So thank you for American Physics Teacher Association give us a solution manual which we have referenced.